So good afternoon, everyone, and thank you, Lucia and the organizers, for putting together this very nice online seminar series. I'd like to discuss the strength evolution of the lower crust today in a sort of a virtual journey through the Wilson cycle. And I like also to acknowledge some of the collaborators that have worked with me over the past few years on this topic, in particular Lucy and Julia, who have worked as postdoc and PhD on related topics. Just a few words about the motivations, really. So the idea is to understand a bit more about the strength of the lithosphere, defined as the ability of the rocks to sustain elastic stresses over geological timescales with negligible flow. We probably are all familiar with the two, let's say, end members strength profiles that we can see in this image by Burgman and Dresen. So one on the left-hand side is a strength profile of the lithosphere that has a wet lower crust, which is supposed to be weak and capable of flowing under low differential stresses, predominantly because it is weak and crystal plasticity and viscous deformation is facilitated under these conditions. On the right-hand side, in contrast, we have the case of a dry lower crust, described in this case by the dislocation creep flow law for dry feldspar, which is particularly strong. So essentially, one of the key controversies of when it comes to strength of the lithosphere is exactly the lower crust. And the main aspect behind this controversy is actually the water content of the lower crust. So a dry lower crust is mechanically strong. So what can we learn about lower crust strength by looking at natural shear zones and different tectonic settings? I'm trying to go through these today. So obviously the deformation behavior and the strength of the lower crust plays a fundamental role when it comes to the architecture of rift. In this example, recent example by Craig and Jackson, they discussed the earthquake depth in the East African rift, more specifically comparing what happens in the Northeast with respect to what happens in the Western and Eastern branch. Western and Eastern branch are characterized by deep crust seismicity, which has been reconciled, let's say, or explained by the occurrence of dry and strong granulites at depth. So the rheological stratification of the lower crust, or the crust in general, clearly plays a fundamental role when it comes to distribution of earthquakes. This has been also discussed by Åke Fagereng in 2013 when investigating the distribution of deep earthquakes in Malawi. And the idea there is that these deep earthquakes that are down to 30, 40 kilometers depth are best explained by a dry and strong mafic lower crust down there, as these earthquakes occur at depth where the temperature, according to this thermal model, is supposedly in excess of 500 degrees. So frictional deformation there requires the buildup of high differential stresses, which is best reconciled with a mafic lower crust. So, okay, we know, we are aware that the rheological stratification, it is increasingly clear really that rheological stratification of the crust and rheological heterogeneities in the crust play a fundamental role in shaping the architecture of rifting or rifted margins. And we have seen this image from Benoit just a while ago, as well as in the localization of the seismicity in rifted margins. But what perhaps is a bit less explored is what is the effect of rifting on rheological evolution of the lower crust. So what can the lower crust, how can the lower crust be modified by rifting and associated metamorphic modifications experienced during rifting? And this is the window that I like to open today. What is the approach that our group uses? Well, we rely on the existence of outstanding natural laboratories. So unfortunately, direct observation of the rheology of the lower crust is difficult because of the paucity of lower crustal exposures. But when they are exposed, these natural laboratories are really outstanding because provide us with direct observations of rheological and metamorphic transitions experienced by the lower crust. In this case, for example, we see a localized shear zone in Lofoten in northern Norway occurring within a dry granulitic facies gabbros, and the shear zone is hydrated. So again, we start to appreciate the role of fluids here into the strength evolution of the lower crust. So when these natural laboratories, these exhumed lower crustal sections even contain pseudotachylites, which are frictional melt produced during seismic slip, they are perhaps even more valuable because they open a window into seismogenic potential of the lower crust. And this is something that I will come back to towards the end of the presentation. And therefore, it will help us understand how these enigmatic lower crustal earthquakes can form, and allow us to reconcile perhaps field observations with existing models for deep crustal seismicity, for example, in the East African Rift. This type of shear zones also allow us to investigate directly rheological transitions in the lower crust. We can see here that ductile shear zones exploit pseudotachylites, and this is something that tells us that earthquakes are really, how can I say, agents of rheological transitions in the otherwise dry and strong lower crust. The key approach here is to rely on microstructures. So we go to the field and then we look at a bunch of thin sections and we interpret the microstructures in terms of deformation mechanisms. And we compare the microstructure in nature with microstructures in experiments. Luckily, they tend to be very similar, which allow us to extrapolate laboratory-derived flow laws or constitutive equations to natural conditions in order to estimate the rheology of natural shear zones. Okay, let's back to rifting. It is well known for decades, really, that high-grade metamorphism, granulite fascias, including partial melting, occurs in the lower crust during rifting due to lithospheric thinning and to the establishment of a high-temperature geothermal gradient. So granulites that develop in this way tend to be characterized by long residence times in the lower crust at fairly constant pressure. So they are called isobarically cooled granulites prior to their emplacement or possible emplacement into orogenic wedges during much later events. And perhaps they are emplaced in the form of extensional alloctons into orogenic belts. And these extensional alloctons often have a fairly well-preserved pre-collisional fabrics, indicating that these fabrics have the potential of survive metastabile in the course of the Wilson cycle. How does this metamorphism work? Well, essentially, lower crustal metamorphism during rifting is characterized by granulite fascious metamorphism and placement of lower crustal bodies. We have seen a fantastic example from Benoit five minutes ago. And the contact metamorphism, also driven by the emplacement of these gabbros, has the potential to modify extensively the lower crust, which can undergo anatexis, but the melt in the lower crust is also likely to escape towards shallower crustal levels. And this is something that I would like to explore a bit more in the next 5 minutes. In order to do so, I will bring you to northern Norway, and more specifically to the Seiland Igneous province. We are not too far from North Cape here. The Seiland Igneous province is a rift-related magmatic suite that emplaced at 570 to 520 million years ago at about 0.6 to 1 GPa depth during a Iapetus rifting, or let's say this is the present-day interpretation for the origin of the Seiland Igneous province. The Seiland Igneous province is predominantly made up of gabbros, different gabbros bodies or sheets separated by paragnesis that localize ductile deformation, or let's say magmatic to solid state deformation, syn lower crustal extensional shearing. On the right hand side, we see an example of a cartoon of this extensional shearing, syn rifting extensional shearing from this very nice paper of Lee et al. What are the rocks here? Is it advancing or not? Okay. Sorry for that. Sorry about that. Okay. The rocks of the Seiland Igneous province are predominantly gabbroic with a nice primary magmatic layering, whereas the host rock, these metasediments that I briefly introduced earlier, are extensively modified by contact metamorphism, partial melting, and deformation, so syn extensional shearing. So let's look into these metasediments. So they are migmatites, they are stromatic migmatites. That includes what we identified as a leucosome-rich domain and a leucosome-poor, essentially a restitic domain. So these rocks are quite interesting because they perhaps tell us or can tell us what happens to the rheology of the migmatitic lower crust with progressive degrees of melt extraction. So partially molten lower crust is expected to be weak. But what happens when most of the melt has been drained out of the system? So in order to investigate this, we have looked specifically into the leucosome poor domain as a proxy for the rheology of the restitic lower crust. Some microstructures here. The microstructure in the leucosomes tells us that the melt forming reaction was dehydration melting of biotite. We have melt pools here reaching K feldspar and biotite inclusions in the garnet. And we also see that in the leucosome poor domain, there is a bit of melt. We can see these melt films surrounding sillimanite porphyroclast, and this melt is synkinematic to shearing because it feels strange shadows. So there was a bit of melt also in the leucosome poor, so probably because it was being progressively expelled from the system through efficient deformation.
Okay, you've had 10 minutes now.
Yeah, thank you. Okay, the pressure and temperature conditions of deformation are around 800 degrees and 0.8 GPa. The amount of water is higher in the leucosome-rich domain. Not surprisingly, the water is preferentially partitioned into the leucosome, whereas the leucosome-poor domain is less, or let's say is water depleted with respect to the leucosome-rich domain. And the volume of melt in the leucosome-poor domain is less than 5% according to our models, which is not sufficient to weaken the system, right? So in Felsing system, at least 7 to 10% volume percent are necessary to weaken the rocks. So this means that the rheology of the restitic rock is really dominated by the solid framework of quartz that is forming more than 70% of it. So at these high grade conditions, the rock is expected to be weak and flow at very low differential stresses because it's really high temperature. However, we have evidence for high creep strength in the leucosome poor domain in the restite in the form of quartz microstructures. For those of you who are more familiar with quartz microstructure, perhaps you can really identify bulging recrystallization here or fine bulges along suture grain boundaries. These are microstructure characteristic of high stresses during dislocation creep. So we used EBSD to investigate the quartz microstructure and grain size better. Especially in order to apply paleopiezometry, which is the empirical relationship between recrystallized grain size of quartz and flow stress. You see the diagram here on the left-hand side. So we measured about 1,000 grains of quartz. The average grain size of about 16 microns gives stresses in excess of 70 megapascal, 70 to 100 megapascal during flow. So now we have the temperature and we have the differential stresses, right? So then we can plot the flow laws for quartz, the available flow law for quartz for geological strain rates, and we can compare the available flow laws, so the prediction of rheology of quartz during the formation in the Seiland Igneous province with our measurements. So essentially, what we conclude here is that our quartz is really strong. Our rocks are very, very strong. They plot up here, whereas they should plot down here. So these rocks should flow really at 1 to 10 MPAs, where they flow at 100 MPa. But we know that dry quartz is mechanically strong. We know it from the 60s, where Griggs and Blachik deformed dry quartz and found out that the yield strength was very, very high. So then we measure the intracrystalline water content of our quartz grains, and this is in fact quite dry. Let's say comparable to the dry conditions of the Brazilian quartz used in the experiments. So quartz in the residual granulites is dry and therefore it is strong. So this made us conclude that the removal of partial melt is a very efficient mechanism to form a strong lower crust, to dehydrate and harden the lower crust. So despite prolonged weakness during migmatitic deformation, melting and melt loss ultimately result in a strengthening and a dehydration of the lower crust. So how can we deform this strong and dry lower crust? So we think we can deform it only if we infiltrate fluids, and this requires earthquakes, which can be similar to what we observe in the present day seismicity underneath Himalaya, where earthquakes conceivably would develop pseudotachylites and perhaps mylonites if rheological transitions are kicked off. So we have one of these examples in the Western Norway, in near Bergen, where the Jotun-Lindås nappe, which was probably either a microcontinent or an extension of a lochton, is made up entirely of or predominantly by granulites, and it is transformed into eclogites only along fractures filled with pseudotachylites, so along earthquakes. These are examples of pseudotachylites becoming ultramylonites from Lofoten and from the Bergen arcs, where this rheological transition is superbly exposed. So this transition, in our opinion, is driven by the fine grain size of pseudotachylites, which is particularly prone to undergo diffusive mass transfer, diffusion creep, and grain boundary sliding, and therefore to weaken the rock. And I leave you with a conclusion on screen, really, that the idea here is that granulites are really a nice, provide us with a nice journey through the rheological evolution of the lower crust, through the Wilson cycle, from dehydration, hardening to hydration and weakening through earthquakes, deformation in collisional settings. Thank you.
Thank you, Luca. So we have a couple of minutes for questions. So I see there's one in the chat from Jean-Baptiste Coyle. So I'll just read it. He says, "Hi, Luca. Thank you very much for a very interesting presentation. I have probably asked already, but could the Seiland in Igneous province have been emplaced during back arc extension?"
Good question. I assume it could, but that would require further research. At the moment, I think the dominant model for the SIP is that it emplaced during the Iapetus rifting event.
Okay, I see also that Robert's raised his hand.
Yes, this is Bob Winch
Bob.
asking a question. Hello, I'm interested to know how confident you are, especially in the quartz microstructures, that they were produced at the maximum depths that you suppose, and that they were not that microstructures were not modified during exhumation, during the exhumation.
Thanks, Bob, for the question. I went too fast there. Thank you. We are fairly confident because along the quartz grain boundaries of the fine grain quartz, there are sillimanite needles preserved. And we also measure the titanium in quartz, in the fine grain quartz, and it is fairly high in concentration. So we apply titanium in quartz thermometry, and this gave us results consistent with pseudosection, so temperature higher than 750.
Okay, and one more quick question. I hope it's quick. The earthquakes below 20 to or 25 kilometers, is there any possibility that these are caused by hydrofracking? That is the production of a little magma, and that gives you hydrofracks.
I suppose it's possible, but we don't see the geological record of that, because all the pseudotachylites in the deep crust that we see are really bone dry. So they are within rocks that are totally dry. So there is no evidence for an active role of fluids in fracturing. So the mylonites have a bit of water infiltration, but we are talking about minute amounts. So we think that the origin of earthquakes and pseudotachylites there is by failure, frictional failure of dry, strong lower crust under transiently high, very high differential stresses.
Okay, thank you.
You're welcome.
Thank you.